Welcome to AI Paper Slop. Today we're diving straight into context-weighted discrete flow matching by Daniel Chernyavsky, Daniel Severo, and Karen Ulrich from Metafair and the University of Amsterdam. If you are currently relying on standard discrete flow matching or DFM to generate text or molecules, here is the zero fluff rundown. Standard DFM basically treats all masked tokens totally equally during generation. But the difficulty of predicting any given token actually relies heavily on the density of its local context.
Right, which makes total intuitive sense when you think about it.
Exactly. So this paper introduces a really simple weighting mechanism based on that available local context. And you can apply it at inference time with literally zero fine-tuning or at training time via a scaled cross-entropy loss. The results.
Yeah.
A massive 63% reduction in generative perplexity on the OpenWebText dataset.
And up to 2.8 times more valid molecules generated on the QM9 dataset, which is huge.
Yeah, and it does all of this while completely maintaining the flexibility of any order generation, matching strong semi-autoregressive baselines.
So today, we are going to unpack the underlying continuous-time Markov chain math that actually makes this possible. We'll dig into the empirical proofs and explore exactly how these context-weighted solvers operate across, totally different compute regimes.
Because to really appreciate this solution, we first need to isolate exactly why standard DFM is just, leaving so much performance on the table during token prediction. In standard DFM, the probability path and the factorized training objective essentially break generation down into coordinate-wise prediction problems.
Right, and the contrast with traditional autoregressive models is really the core of the issue here. I mean, an autoregressive model like a standard GPT has it pretty easy. It predicts the next token conditioned on a fixed known prefix. It just reads left to right.
It has a stable foundation to build on.
Exactly. But DFM and discrete diffusion models operate entirely differently. They effectively marginalize over all possible token order permutations. So, unlike GPT, they have to predict tokens under these wildly different arbitrary partial contexts.
Which causes this extreme variation in prediction difficulty. Because, some tokens are heavily constrained by the tokens right next to them, making them super easy, while others are just completely ambiguous. I like to compare it to playing Wheel of Fortune or Hangman.
Oh, yeah, that's a perfect analogy.
Right, like guessing a letter when the board is totally blank, just 4 empty squares, that is a highly ambiguous high-entropy situation. It's a total shot in the dark. But guessing a letter when the board says little blank riding hood, the target uncertainty there is basically zero. You know exactly what it is.
You do. But standard DFM literally looks at both of those scenarios and says, yep, these get the exact same weight in the loss function.
It's crazy.
It is mathematically super inefficient. And historically, the field has tried to mitigate this by forcing structured generation orders, right? Like blockwise decoding, the hard code rule so the model isn't just, guessing in the dark all the time.
But doing that completely kills the main advantage of DFM.
Exactly. It kills the flexibility of order-agnostic generation. The moment you force a specific order, you lose that parallel, flexible generation.
So the Wheel of Fortune analogy makes intuitive sense, but obviously in architecture design, intuition isn't enough. How do the authors actually mathematically prove that local context is the right proxy for prediction difficulty?
They took a really cool empirical approach. They used a pre-trained DFM on the OpenWebText corpus, sampled partially masked states, and then measured 2 very specific things. First, the model's prediction entropy, basically how uncertain the model is, and second, the negative log likelihood, or NLL.
Okay, so they took those 2 metrics and they plotted them against what?
Against the number of unmasked neighbors within a fixed local window. I think they used a radius of 16.
A vicinity radius of 16 tokens, yeah.
And the finding is just this perfectly monotonic downward curve. Both entropy and NLL decrease steadily as the number of unmasked neighbors increases. Nearby observed tokens literally make predictions less uncertain and more accurate.
Right. And to translate that into, actual training efficiency, we have to look at the expected per token loss. The paper breaks that decomposition down into irreducible uncertainty, which is just intrinsic ambiguity plus reducible model error.
Right, the reducible part being where the model actually has something to learn.
But wait, let me push back on that for a second. If a token has really high entropy, isn't that just because the model is confused? And usually in ML, when a model is confused by hard data, we want to force it to learn those hard examples, right? Why shouldn't we force the model to learn those hard tokens equally?
That's a super common assumption, but it relies on all high entropy being reducible error, and here it's just not. For those high entropy coordinates, like the blank Wheel of Fortune board, a massive part of the loss is purely intrinsic ambiguity. That's the irreducible part.
Because there's literally no context yet.
Exactly. There is no underlying pattern to learn. So forcing the model to update based on a single sampled target in an ambiguous context, it just feeds it a noisy, uninformative training signal. Weighting really needs to emphasize the reducible model error, which you only find in those low entropy, highly contextualized tokens.
Because that's where the model actually has enough information to learn a real pattern.
Right.
Okay, so knowing that local context is basically a perfect proxy for uncertainty, the authors first apply this strictly at inference time, which is awesome because it means you can upgrade existing pre-trained models literally for free.
Yeah, it's a great free lunch. They essentially modify the continuous-time Markov chain transition dynamics so that they depend directly on local context. So you just apply a multiplicative weight directly into each coordinate of the Euler solver.
And they introduce two distinct solvers for this, right?
They do. First, there's the neighbor-weighted solver. That one is super simple. It just uses the raw count of unmasked tokens in a local window. And then there's the entropy-weighted solver, which uses the token-level predictive entropy that the model can calculate at test time.
But hold on, if we arbitrarily change the transition rates of the Markov chain based on local context, like we're just dynamically speeding up some tokens and slowing down others, don't we completely break the probability path? I mean, how do we guarantee the model actually reaches the final data distribution?
That is the big mathematical hurdle, and they address it perfectly in Theorem 1. The endpoint constraints of the path are actually completely preserved as long as you follow one rule.
Which is?
The weights you apply have to average out to exactly 1 over the currently masked coordinates.
Oh, I see. So if you speed up the update rate for one token, you just have to slow down another token to balance it out.
Exactly. That preserves the total update rate. So the overall distribution of how many tokens get updated remains identical to the standard path. And furthermore, if the rule you use is equivariant under circular shifts, basically meaning you treat all positions symmetrically, the per-coordinate marginals precisely match the standard convex path.
That is incredibly elegant. So hacking the Euler solver at inference is great. But ultimately, the goal is to bake this inductive bias directly into the training process itself.
Right, because you want the model to learn this prioritization from scratch.
So they introduce Scaled Cross-Entropy, or SCE, and this basically acts as a plug-in alternative to the standard DFM objective. It just upweights the well-conditioned coordinates and downweights the ambiguous ones right during training.
But doing that creates a massive technical problem for the training algorithm.
Because of the sampling, right?
Yeah. Normally, standard DFM allows for simulation-free sampling because the token values are conditionally independent. You can jump to any point in time. But with this new context-weighted path, the tokens are no longer independent. The update of one token depends on its neighbors.
Right. So normally, if you have interdependent tokens, you'd be forced to do exact chronological simulation, which would just totally nuke your training throughput.
It would be unbearably slow. But they introduce Algorithm 1, which uses a really clever mathematical trick. Even though the specific tokens are interdependent, the total number of unmasked tokens at any given time still follows a known binomial distribution.
Oh, wait, so they separate the how many from the which ones?
That is exactly it. Algorithm 1 first samples the total number of unmasked tokens from that binomial distribution. And once it knows how many tokens are unmasked, it sequentially updates the masked tokens one by one, picking them based on the context weights.
Wow, so they achieve exact token-wise sampling with just ON complexity instead of simulating the whole time series.
Yeah. Exactly. It's ON sequential complexity, which totally bypasses that chronological simulation trap.
But let me ask you this. Looking at existing discrete diffusion loss functions like the Bregman divergence or NLBO, they already scale the loss by a time coefficient, right? So if we already have time scaling baked into the field, why do we even need scaled cross-entropy?
Because there is a huge difference between global context and local context. Time scaling, like an LBO, only accounts for global context. It treats heavily noised states differently than lightly noised states overall. But, and this is the key, it treats two masked tokens at the exact same time step identically.
Even if one of those masked tokens has like 10 visible neighbors right next to it, and the other one is completely isolated with 0 neighbors.
Right. And LBO just applies a blunt global multiplier. SCE targets the local context, which gives the model a much sharper localized learning signal.
Yeah, when you look at the benchmarks, that sharper signal clearly pays off. I mean, the OpenWebText dataset uses the uniform source SCE, reduces generative perplexity from 82.17 all the way down to 30.20. That is a 63% reduction.
It's massive, and it improves the MAUVE score from 0.628 up to 0.777.
Which basically means it totally closes the gap with strong semi-autoregressive block diffusion baselines like BD3LM. But it still retains the any-order generation flexibility. It just absolutely crushes standard baselines like SED and MDLM.
Yeah, and the results get even more interesting when we look at low data regimes. They tested this on the QM9 dataset, generating molecular structures, SMILE strings.
Right, and molecules are totally different from text.
Very different. And in low data regimes, a neural network's internal uncertainty estimates get incredibly noisy. The model just doesn't know what it doesn't know.
Which I assume breaks the entropy-weighted solver, since it relies on the model's own predictive entropy.
Exactly. The entropy-weighted solver struggles there because its core signal is garbage. But the neighbor-weighted sampler, it vastly outperformed everything. Just relying on the physical count of neighbors yielded 2.8 times more valid molecules and 1.9 times more novel molecules out of 124 samples.
That is wild. Just counting the neighbors gives you nearly triple the valid molecules.
Yeah, and we see a similar divide when we look at different compute regimes, specifically the number of function evaluations, or NFE.
Right, the number of steps the model takes to generate the output.
Yeah, so at a really low NFE, where you have a highly constrained compute budget, the entropy-weighted solver is actually better. Because with very few steps, relying purely on neighbors can create local inconsistencies. But once you scale up to a high NFE, anything greater than 512, the neighbor-weighted sampler completely dominates again.
Because it has enough steps to iteratively refine those local contexts.
Exactly.
And they also did an ablation study to find the sweet spot for that local context, right? Like, how big should the neighborhood actually be?
Yeah, they tested the vicinity radius, they call it RR for the neighbor-weighted scaling, and they found that a radius of 3 provides the absolute best MAUVE peak.
So looking 3 tokens to the left and right.
Right. If the radius is too small, it just doesn't capture enough context. But if it's too large, it starts taking in irrelevant distant tokens, which makes the model overly confident and kills the diversity. So R equals 3 is the perfect balance between coherence and diversity.
That makes perfect sense. And before we wrap up, it's worth noting for anyone implementing this context-weighted sampling is completely complementary to predictor-corrector schemes.
Oh, absolutely.
You don't have to choose between them. You can just stack them together for even lower generative perplexity. It's a completely modular upgrade.
It is. And, looking at the limitations section of the paper, it actually leaves us with a really provocative thought to mull over.
What's that?
Well, this paper undeniably proved the immense value of local context waiting on one-dimensional discrete sequences. Text strings, SMILE strings, they are all 1D. You just read them left to right.
Right. The definition of a neighbor is incredibly straightforward in 1D. It's just the token next to you.
Exactly. But how might this simple local context proxy behave when we try to adapt it to high-dimensional data?
Oh, like generating 2D images with visual patches.
Yeah, or complex 3D volumetric structures for things like spatial drug discovery. In a 3D grid, a neighborhood isn't just a simple linear count anymore. The geometry is vastly more complex, and defining that available context becomes highly nonlinear.
That's a huge mathematically unsolved problem, actually. Mapping the math to preserve those marginal probabilities across a complex 3D neighborhood shift.
Right. But if someone can figure out how to adapt this context-aware Markov chain modification to those higher dimensions, we could theoretically unlock the exact same 60+% perplexity reductions in spatial generation that we just saw in language.
Which would be a total game changer for spatial AI. It's wild to think we started today talking about models that were just hopelessly guessing in the dark on blank sequences. And just by giving the mathematically easy tokens priority, the prediction accuracy absolutely skyrockets. It's a great reminder that sometimes the biggest architectural leaps aren't about brute forcing more compute, but just adjusting the math to reflect how context actually works.
Completely agree.
Well, we will leave you to mull over that 3D scaling problem. Thanks for joining us on this breakdown, and we will catch you on the next deep dive into the research.